We're going to study the design of other gear types rather than just spur gears now. But let's start with our demotivation poster. Affirmation, instilling the self-confidence kids will need to carry them through all the failure they'll experience because they weren't taught competence instead. I really like that one. I think these are hilarious. So, trying to keep some traditions rolling, and that's one of them. So we're going to study the design of helical, bevel, worm gears. Those are the types that we're going to study beyond the plain spur gears. And you can see some very large high-speed gearing for ships sitting here on a dock apparently, ready for installation. Either that or they're being repaired. I'm not sure which the case is. But these are very large gears. They're a particular type, and you'll know the type once we get there. They're a type of helical gear. What is a helical gear? It typically operates with teeth that are skewed relative to the shaft. So they typically operate on parallel shafts, but they can be operated on shafts that are not running at the same angle. But that's not very common. So you see the upper left figure, you've got a left hand and a right hand helix running together. And if you have these gears running together at an angle, then they'll have the same hand, be it right hand or left hand. But again, this is not common because there's so much sliding that occurs, and really helical gears are not optimized for running at skewed angles. Usually if they do, they are at a right angle to one another, and they can't transfer a whole lot of load. Now the handedness of a gear is something you need to understand. If you look at the figure at the bottom of the slide, you'll notice a spur gear on the left. And the idea is that if you were to wrap your thumb in the natural direction of the tooth, your fingers would point in the direction that the teeth move. Okay, so you can see the handedness, the right-handedness and left-handedness of the helical gear, and I don't have a better way to describe it than that. But one thing about it, you have to have a right-handed and left-handed gear to operate together on parallel shafts. And of course, the other things have to match as well. The helix angle, for example. The helix angle is really just the angle of the teeth relative to the axis of the gear. Of course, the diametral pitch has to match. In other words, the tooth size has to match. Otherwise, the gears won't run together. Now, most helix angles, in other words, the angle of the gear teeth from spur, which is straight, that would be a 0-degree helix, increasing is usually from about 15 to 35 degrees. Now, some of the advantages of a helical set is, number one, that you have a higher contact ratio. What that means is that there are more teeth in contact at the same time. And this should make sense. If you consider the helical gears on the previous slide, you'll notice that some of the teeth actually, part of the tooth was in mesh and part of it was not because it hadn't reached the mesh area yet. And so the fact that there's a high contact ratio really just means that there's more teeth in contact. And because of the way the teeth are angled with respect to the gear body, the fact is that the pressure or the force is applied from one tooth gradually along the face of the tooth. So this is a huge advantage. Now it does result in a problematic byproduct. The problem is that this shape of tooth or the angle of the tooth causes there to be a force on the gear to make the gear slide along the length of the shaft. And that's problematic. We don't want that to happen, obviously. One way to overcome this problem is to simply include two separate helical gears in one body with two separate handedness. Right, a right hand and a left hand, and that way the thrust forces will cancel out. Now these are called herringbone gears, and those were the types of gears that you saw at the beginning of the slide, the picture of the very large gears. There are conventional herringbone gears, they're staggered, there's continuous, and just depending on the application you can choose what you need. Continuous is the most difficult to make because getting into that point in the middle is hard. But staggered gives you a little bit more advantage in terms of a little bit smoother contact and engagement between the teeth. Conventional just makes two separate helixes and puts them together essentially. So that's herringbone gears, but they're not especially common. Let's consider the forces on the helical gear teeth. This is a really important figure to wrap your head around. What's being shown here is the body of a gear without the teeth themselves. They're just lines on the surface of this cylinder to represent the teeth. Now remember that we always put oil between gear teeth, and so the gear teeth can't have any friction forces that are perpendicular to the normal of the surface, or in other words, along the surface. We can't have any force. So the only force that can exist is a normal force. Now, let's start off by looking at the normal plane. The normal plane is highlighted here in blue, and it contains the normal force. So you see that it's at an angle. It's normal to the tooth itself, or this plane is normal to the tooth. So this is the normal plane. It's pulled off down here at the bottom. And if you were to look at this plane straight on, or square to it, you would see the true normal force. That's that dashed arrow in the middle of the rectangle there. And notice that it is at an angle, phi. Now that phi has a subscript n, and that is called the normal pressure angle. So that's an angle in the normal plane, so it's a normal pressure angle. Now the part of what we care about is the horizontal piece of this. Okay, so if we take the normal force and break it up into horizontal and vertical components, we'll get a radial force, and that radial force tends to push the gear away from whatever it's meshing with. And then we get a horizontal piece that is almost what we want. Now notice this horizontal piece is not exactly in the direction we want. There's a component of this horizontal force that tends to generate the axial force. And part of this is the tangential force, which is the whole point of having the gear in the first place. But there are some equations here to relate the tangential, normal, and radial components. There's our normal force. You can see it in that plane. There it is highlighted when we look directly at the plane. And like I said, it breaks up into two components. One component that's going to be broken up further, because that component is still at an angle to the teeth, and another component that tends to separate gears from one another that are in mesh. If we consider the tangential plane, remember I said we care quite a lot about that purple vector, that component that was normal to the tooth but in the x direction. Well, let's move down to the tangential plane. The tangential plane contains that entire vector, that purple vector that's still highlighted there. The tangential plane is the top figure on the right. Now, in the tangential plane, what we're doing is we're looking from the top down. We're looking in the radial direction at the gear. The piece that goes from corner to corner, the diagonal, that's what I was looking for, the diagonal line there represents that purple vector that we had before. It's the same thing. There's no difference. And, oh, by the way, let me note that symbol psi, where it says W sub t over cosine of psi, that Greek letter psi is the helix angle. It's the angle of the teeth with respect to the axis of the gear. So anyway, here's that force that I said we want to break up further, and we'll break it up into a tangential piece and an axial piece. So you see the tangential piece there. That's the piece. That red vector is the whole point in having the gear in the first place, because it's that force that tends to rotate the gear about the gear's axis. The axial force comes along for the ride. In other words, the axial force is there because the teeth are at the helix angle. And again, just like the radial component of force, this axial component is an undesirable force that has to be supported against. Otherwise, the gear will move axially along the length of the shaft that it's riding on. So there's the axial force back over on the gear in blue. And let's see what else we can analyze. There's one more plane to consider, and that's called the transverse plane. So you see it there, and it's of course the last figure. Now the transverse plane has a force in it that we want to decompose as well. This force is really just the projection of the normal force. Yeah, I'll call it the normal force. That's what it is. But it's, I guess probably a better word would be the true normal force. I don't want to confuse you with normal force from statics or dynamics. So it's the true normal force. It's the total force on the gear tooth. What we're doing is projecting that force from the normal plane into the transverse plane. So you see it there in sort of an orange color. Okay. Now, that vector can also be broken up into, again, the tangential load, which is, again, what we want, right? Because the tangential load is in the transverse plane, just as it is in the tangential plane, and the radial force. Now, we've already seen the radial force. We saw that in the normal plane. But you can find it here as well by decomposing that orange vector, that projected true normal force. Now, notice that the angle of this vector with respect to horizontal is phi sub t instead of phi sub n. That is called the transverse pressure angle. Now, there is a relationship between the transverse and the normal pressure angle. I don't remember if I have it in the slides. I don't believe I do. You should find it in your textbook, and you should be following along in your textbook because all of this is in your book as well. So don't be confused between phi sub t and phi sub n. They are different but related things, and of course they're related by the helix angle. So find that equation and make sure you highlight it. I'm sure I'll come across it in the example problems. Okay, so psi is the helix angle of the teeth. Phi is the pressure angle. That's due to the involute tooth profile. But notice that you would see two different forms of the teeth depending on which plane you use to cut it. For example, if you use the transverse plane, the one we still have highlighted in the middle, you'll see a tooth that is a thicker tooth, right? Because you're cutting the tooth at an angle to the tooth, so it will look wider. And that, of course, is expressed in that little form down and to the left that really it looks like all of the arrows are pointing to in that transverse plane. In the normal plane, you'd see the true profile of the tooth because you're cutting the tooth normal to the tooth itself. So Wn, some terminology just to recap, is the true normal force. Wt is the tangential force. Again, that's the whole reason for having this gear in the first place. W sub r is the radial force, and it is a side effect of the involute profile of the tooth. And the axial load, W sub x, that axial force, is a side effect of the helix angle and the fact that these teeth are not like spur gear teeth. They're at an angle. Now, how do we design these teeth? Well, we have to consider bending stress and compressive stress in these teeth as well. And so we're not really calculating the stress itself. We're approximating the stress in the gear teeth, and that's why we call it a bending stress number and not a stress. Now, the geometry factors, J, are different for helical gears than they are for spur gears. So you'll have to note my little text down there at the bottom that says on page 385 through 387 you'll find several tables, that give you the geometry factors J for helical gear teeth. Now the factors, the K factors, the overload, the size, the velocity, all those factors are exactly the same as they are for spur gears. So we can just reference back to that information in the previous chapter, chapter 9, and use it. Bevel gears are another class of gearing that we're interested in designing. There are straight bevels, spiral bevels, zero spiral bevels, hypoids, and other flavors, if you will, of what you might have thought were just bevel gears. We're not going to study all of these. Here's some pictures of what these things actually look like. We're going to concentrate our efforts on the straight bevel gear. That's the one that we'll be able to design. The others, we won't find any design methods in our class for these. Now, bevel gears usually intersect at right angles. They don't have to. You can make them intersect at other angles, but that's not common. And if both gears are the same, then the whole purpose of having bevel gears is to turn a corner. In that case, they're called miter gears. So they would have the same number of teeth and so forth, and not give rise to a speed increase or a speed reduction. Now, if there are two bevel gears meshing together and they're not at right angles, they're at some other angle, then they're called angular bevel gears. The U.S. standard bevel gears system is the Gleason bevel gear system. It's based on a 20-degree pressure angle. One thing to note about bevel gears that is different between spur and helical gears and bevels, bevel gears are the first class of gearing where the pinion and the gear have to be matched to one another. You can't go buy a gear, a bevel gear of one size that has, say, 48 teeth, and say, you know what, that pinion I bought with 12 teeth won't work. I'm going to just move it up to an 18-tooth pinion. That doesn't work. The geometry for bevel gears doesn't work that way. And you'll see that in the example problems as I design a bevel gear set. Hypoid gears are not really a true bevel. They kind of look like one. They were developed by the auto industry, mainly for rear differentials. And just like spur gears are to bevel gears, hypoid gears are to helical gears. And the angled tooth form, or the curved tooth form, gives a nice smooth engagement and is less noisy and can transmit more power and so forth. So you can do all kinds of interesting things with these. A true hypoid has the shafts offset. If it's a spiral bevel gear, then the shafts of the gear and the pinion intersect theoretically at a point. But we're not going to deal with those. We are interested in the forces on the bevel gear teeth, because those forces are what would tend to cause the teeth to fail. So you have to think through this. If you look at the figure, not the photo, but the figure on the lower left, you'll notice the gear has 48 teeth, the pinion has 16 teeth. That symbol gamma is the cone angle, or the half cone angle. I don't know the actual name, I don't recall right now, but you'll notice that the teeth of both these, well, both the gear and the pinion, are on the surface of a cone. And that angle, gamma, is an important angle. As a matter of fact, in the geometry section of your text, where they're talking about the geometry of bevel gears, they tend to use the symbol, well, they always use the symbol lowercase gamma for the cone angle on the pinion, and uppercase gamma for the cone angle on the gear. So make sure you're familiar with the geometry. That's a general approach, I guess, to bevel gears. What they usually take, they'll use lowercase letters to indicate the pinion and uppercase letters to indicate the gear, at least in the context of bevel gears. Now, if we extract these two gears and draw a couple of views so that we can look at them from the top, well, face on or side, go over to the right-hand set of figures and you'll notice that you've got a front and side view of the pinion, and then going down, a top and side view of the gear. Now, if you think about how these two touch each other and mesh together, you might want to look at the side views of both and ignore the front-on views for the moment. Now, you can imagine the pinion moving down, or the gear moving up, to mesh with one another. And so the axial force on the gear, look at the lower figure, W sub xg, that axial force on the gear that tends to try and push the gear along its shaft, comes from the radial load on the pinion. You see W sub xg and W sub rp, look at the upper figure, W sub rp, those are the same force. And W sub xp in the upper side figure, okay, you see that, the force that tends to cause the pinion to move along its axis, W sub xp is equal and opposite to WRG, in other words, the gear radial load in the lower side figure of the gear. The only thing that matches, the load that matches between the pinion and the gear, is the tangential load. So now look at the upper views of the pinion and the gear and notice W sub tg and W sub TP. Those two forces are the two tangential forces, and they are equal and opposite. That's the load that we want in order to transfer power between the two gears. Now, the behavior of the gears depends on how well they are supported. Bevel gears lend themselves to being cantilevered, so put out on the end of the shaft, and you know that, or you should know that the ends of shafts can deflect more generally than the center of the shaft where it's straddled. So one thing you can actually do, you can actually straddle mount bevel gears. And that's the ideal situation. So what you see here is a bevel gear in cross-section near the lower part of the figure. Of course, it's riding on a shaft. That shaft is connected to a bearing D it's called, which then goes to the housing to support any loads. Now you'll notice at the other end of the shaft is bearing C. And those two bearings straddle the gear, and so they support the shaft. And it's not easy to see, it's not obvious, but the housing that's around bearing C, just that little bit of crosshatch out at the edges, that would somehow connect to the rest of the frame that's holding all of this gearing and shafting in place, and connect back to the same frame that's holding bearing D in place. But this is a straddle mounted gear. Similarly, in this case, the pinion is straddle mounted. So look over to the right and you'll see bearing A and bearing B that are riding on the shaft with the pinion riding between those two bearings and therefore being straddle mounted. So this is the ideal situation, but it's not always the case. You'll notice in the example problems that the way that the bearings are mounted, whether straddle mounted or cantilevered or one straddle mounted and the other one cantilevered, makes a difference in the design of the gearing and what's required. So the first thing to do in order to solve some of these problems is to first of all draw free body diagrams to show the tangential, radial, and axial loads applied. Then you would calculate the bending stresses and deflections, calculate the loads on the bearings, and then of course it's ideal for bevel gears themselves to have stiff shafts and rigid mountings. Now the first 3 points here are with respect to sizing a shaft. So we already studied shaft sizing in the course, and I didn't go through a lot of detail about how you would calculate loads from gears, so we're sort of backfilling that now. But these loads that are applied to the gears are also applied to the shafts, and the shafts are what actually have to resist those loads. What about the stress in bevel gear teeth? Well, you'll notice that the stress equation here is a little bit different. Now this is the bending stress, this is not the contact stress. But it's a similar procedure to what we have for spur and helical gears. It's just that the factors are a little different. So you'll need to see the page numbers I've referenced, and again we'll go through these in the example problems. You may want to tab them for the time being so that you can find them. But the setup is similar but a little bit different. Some of the factors are the same, some are different, and we'll explore those details in the example problems. Worm gears are used when you need a very large reduction in speed, and typically the shafts are at 90 degrees to one another. Now, what you'll notice is in the lower left-hand figures, there's a large round thing and a smaller threaded thing. Most people would call that threaded thing a worm gear before they learned about worm gears. That's not the worm gear. That is called the worm. The threaded item is called the worm. The item that has teeth, like a gear, is called the worm gear. So that larger round item is the worm gear. Now, you might look at this and say, okay, well that's interesting, but how on earth would I calculate the speed ratio between the two? Well, you might be tempted to count what appears to be the number of helixes on the worm. So if you count it, you can see it in that front figure there. Let's see, it looks like there's 1, 2, 3, 4, 5. So you might say, well, it looks like it's a 5 worm, and maybe the gear has a certain number of teeth that I could count. Of course, they're simplified, so they're not shown. That's not how you do it. What you do instead is you trace one helix all the way around. That is one tooth, or effectively one thread. Now, it is possible to have more than one helix on the worm. Look over at the right-hand pictures, and you'll see a single start worm, and what this means is wherever the thread starts, if you trace your finger around it, you'll go on your finger will touch each successive wind or coil in the helix. There are double start worms. If you look at the figure in the center there, you'll notice that there are 2 starts for 2 totally separate helixes. They have the same angle, same size thread, everything's the same except that they are a double helix. It's possible to have a triple start. So how do you count the number of, you would think teeth, but they're actually threads on a worm? Well, it's just however many starts there are. All you got to do is look at the end of it, count how many starts there are for helixes, and the number of helix starts is the number of worm threads. So in the figure on the left, that worm actually has 2 separate helixes, and so it is a double thread or a double start worm. It's just not shown. So in other words, if you were to start, say, on that left-hand start that you can see and trace it around, you would actually not encounter the very next thread. You would encounter the thread following that. There's a difference here between what's called the lead and what's called the axial pitch. P sub x is the axial pitch, and that's always just the difference, the distance between 2 adjacent threads. Okay, not necessarily the distance from one point on one thread to the same point on that same thread. Okay, L, the lead, is the distance that I just described instead. So it's the distance from one point on a helix to that same point on that same helix where it occurs again. And now, since this is a double start worm, the lead is simply twice the axial pitch. And you might say, well, okay, that's fine, but why would I care? Well, think about turning the worm one complete revolution. If this is a double start worm, how far will the gear teeth have to move? Well, they'll have to move by the lead, right? So essentially the gear teeth won't just index one tooth, they'll index two teeth. And so that's why it's important to understand this. So anyway, most of the time, most worms have a single start, and so the velocity ratio is calculated as 1 versus the number of teeth on the gear itself. Now, the way that the worm is designed can be improved. Instead of just having straight gear teeth and straight worm threads, what you can do is design them to include enveloping. And so you'll see in the upper left-hand corner, that is an example with no enveloping at all. If we move to the right top CAD drawing, you'll see that we've got the worm gear enveloping. So the teeth on the worm gear, instead of being straight like on a spur gear, those teeth are sort of cupped in. Now the reason for this is so that the teeth can kind of reach around and get into the threads on the worm. And what this does is it increases the amount of contact area and therefore the strength of the teeth. Now the other option is to make the worm envelop the gear. So lower left-hand CAD drawing, you'll see a worm where the worm threads envelop or wrap around a portion of the worm gear. Now a double enveloping set is in the lower right-hand corner CAD drawing, and both the worm gear and the worm envelop one another. And of course this is the strongest but also the most complicated and most expensive. The photo that I've included is actually an example of this sort of set. So you can see the sort of hourglass shape of the worm. It's hard to see, but you can actually see the cupped shape of the gear teeth on the worm gear. And in fact, you might think, well, it looks like these are two different materials. Well, they actually are. In worm gear design, what's commonly done is the worm is made out of steel and the gear is made out of a material that is intentionally weaker. It's made out of bronze or brass typically. And the reason for that is partially for wear, because there is a lot of rubbing between the worm threads and the gear teeth, but also because we want to be able to design this, and predicting the worm's behavior and performance in life is extremely difficult. But if you make the gear the weaker material, predicting its life and performance is a little more straightforward, a little easier, and you'll see that in example problems. Now notice that it's very rare to see the upper left CAD example where neither the gear nor the worm envelop the other. That's very rare. If you have a Lego set with worm gears and, well, with gears and worms, you'll notice that neither one envelop, and that would be an example of this. However, what is exceedingly common is to have the worm gear envelop the worm. That is very, very common, and it's hard to find a set that doesn't have that feature. In fact, the lower left-hand example is rare for that same reason. Simply having the gear teeth envelop the worm is beneficial and frequently adequate. So the left-hand column of CAD drawings is not common. The two on the right-hand side are much more common. Of course, the upper one is what you normally get, and then the lower one is expensive. Now the lead angle is defined by, imagine taking a thread from the worm and just unwrapping it. So one complete revolution of a thread, just unwrap it, and you can see there then you would form a triangular type shape with the length of the thread being the hypotenuse, the lead angle being defined as lambda. I was trying to remember the name of that symbol. And then the lead is on the left. That's the height of the triangle. That's the distance from the same point on the thread to the same point one revolution later. And then the pitch is just pi times the diameter of the worm. These sets typically operate with the worm turning the worm gear. You don't have the worm gear turn the worm. In other words, you don't back drive these because it's not practical. It doesn't work. There's too much friction and it just simply can't be done. In fact, they can be set up where they are self-locking. In other words, think about it in this case. What if you're riding an elevator? What kind of gear set would you like to have pulling your elevator along? Probably a Wormgear set. The reason is because if the motor fails, let's just say that somehow the shaft on the motor breaks, even with the gear sitting there in its bearing, all the load from the elevator is trying to make the worm turn, and it simply can't. There's just too much friction. So usually these are self-locking. Now, whether or not they are is a function of geometry, lubricant, and materials, and therefore the coefficient of friction. And typically the lead angle is less than 10 degrees or so. The book does recommend a lead angle less than 5 degrees, but the efficiency depends on that angle very heavily, and you'll see that in examples as well. But self-locking design does typically lead to low efficiency. So friction is the primary concern for worm gears when we're designing a worm gear set. The friction depends on the sliding velocity, and there's a coefficient of friction graph that you need on page 410, so I wanted to reference it here. The amount of power that you put into a worm gear set is not the amount you get out. As a matter of fact, worm gear sets are notoriously inefficient. So here we have to start thinking about how much power loss there is. So power goes in, some mechanical power comes out, but there's a significant power loss. And so the efficiency of these types of sets is simply the power you get out, the mechanical power, divided by the power in. The rest of it just goes to heat and loss. There are equations for this, and page numbers 410 is particularly useful. You'll see that in examples again. So worm gear systems are limited by pitting, wear, and thermal considerations. In other words, they generate so much thermal energy that they can overheat. In fact, you'll notice that a lot of gear casings for worm gear sets have fins on them for dissipating heat. Now, the tooth strength is approximate. The method we're using, it's not addressed by the AGMA. And again, we make the worm out of the stronger material because we're better at calculating the stresses in the worm gear. And so we assume failure will occur in the worm gear before the worm, and that way we can predict it and control it and make our worm sets last a predictable amount of time. And of course, the other reason for having steel and bronze running together is for wear considerations. Now, this bending stress that we're using here is just approximate, as I said. There are some terms in here. The dynamic load is included. The Lewis form factor is Y. This does harken back to the Lewis equation for spur gear teeth. The face width of the gear, now this is not the face width of the worm, this is the face width of the worm gear, that's F, and Pn is the normal circular pitch, and you'll see all of this again in example problems. Now, how do we deal with surface pitting, not just bending stress of the teeth, but also the surface forces and the contact stresses? Well, here what we do is we calculate what's called a rated tangential load, W sub TR. And as long as the rating for the gear is greater than the actual load applied to the gear teeth, then it's a good design.